And now in this lecture we'll answer on two questions. In the first question we find out the area of this rectangle ABCD, and in the second question we'll find out the area of this green shape that is inside square ABCD. So we'll start with the first question. In the drawing we have rectangle ABCD, and inside this rectangle ABCD we have this semicircle. This is called PA, that is equal to 6 units in its length. This is line 7 PC, that is equal to 5 units. Again, our mission is to find out the area of this rectangle ABCD. So, because of the fact that ABCD is a rectangle, all those four angles are right angles. So this is a right angle. This is a right angle. This is a right angle. And this is also a right angle. So, in the next step, we'll define the center of this semicircle. This point is point O. We'll define the radius of this semicircle as x. We will define the point of tendency of tangent DC with this semicircle. This point is point M. And we will define the touching point of this semicircle with side AB of rectangle ABCD. This point is point E. So, side point O is the center of this circle, point A is the point of the circle itself, therefore OA is the radius of this semicircle that is equals to x units in its length according to our definition. Likewise, OE is also the radius of this semicircle that is equal to x. We join points O and M together by a straight line. OM is of course the radius of this circle that is equal to x, and because of the fact that the radius OM is equal to x, the radius OM is drawn to point M, that is the point of tendency of tangent DC with this semicircle. And whenever your radius is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If DC is perpendicular to MO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. By doing this construction, we finish with the quadrilateral OMDA. Inside this quadrilateral we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this four pieces again, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore these four pieces again must be equal to 90 degrees in its size. So inside quadrilateral MDAO we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be this rectangle, if not a square. So we refer to this quadrilateral as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle, this small rectangle DMOA, side MO must be equal to the opposite side DA. But MO is x, therefore DA must be also equal to x units, the opposite side DA must be also equal to x units in its length. Likewise, in the big rectangle ABCD, the opposite sides are equal to each other. That is to say, side DA is equal to the opposite side CB. But DA is x, therefore CB must be also equal to x units in its length. In the next step, we'll join points P and A together by a straight line. By joining points P and E, we get peripheral angle APE. Peripheral angle APE subtend on AE, that is the diameter of this semicircle. And according to rule 7, any peripheral angle that subtends on the diameter of the circle or semicircle must be equal to 90 degrees in its size. Therefore, peripheral angle APE is equal to 90 degrees in its size according to rule 7. So, I repeat rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees. In the drawing, we have a circle. AB is the diameter of this circle, and this is peripheral angle ACB that subtends on AB, that is the diameter of this circle, and therefore peripheral angle ACB is equal to 90 degrees inside according to this rule, rule 7. We have already implemented rule 7 in our drawing. Why? Because in our drawing, peripheral angle APE is subtend on AE, that is the diameter of the semicircle, and therefore peripheral angle APE is equal to 90 degrees inside according to rule 7. So in the next step, we define this angle as alpha, and we focus on the right triangle APE. This right triangle APE, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right triangle ABC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first angle must be equal to 90 degrees minus alpha according to the same rule that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that the big triangle ABC, the big right triangle ABC, is similar to this small triangle APE. So I write it down. We prove that the big triangle ABC is similar to this right small triangle APE. So why those two triangles are similar to each other? First of all, this is angle A. This is angle A, that is a common angle that belongs to both. Angle A is a common angle that belongs to both triangles. Angle A belongs to the small right triangle APE, and angle A also belongs to the big right triangle ABC. So we can write down that angle A equals to itself as a common angle that belongs to both triangles. So if you relate to angle A, to this angle A, as it belongs to the right big triangle ABC, it will be defined as angle BAC. And angle A equals to itself. So if we relate to this angle A, as it belongs to the right small triangle APE, it will be defined as angle EAP. So actually, this equation means that angle A equals to itself. We just call to angle A two different names. Angle A equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees, therefore they are equal to each other. So actually, this is angle ABC in the right B triangle ABC. And it is equal to this angle, that is actually angle APE, in the right triangle APE. Repeat again. Angle ABC in the right triangle ABC equals to angle AP in the right triangle AP. They are both equal to 90 degrees, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually, this is angle ACB in the right triangle ABC, and it is equal to this angle. It is actually angle AEP in the right triangle APE. So repeat again. Angle ACB in the right triangle ABC equals to angle AEP in the right triangle APE. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually proved that all the figures of this big right triangle ABC are correspondingly equal to all the figures of this right triangle AP. Therefore, those two right triangles are similar to each other according to angle similarity also. I write it down. We should find out that triangle, the big right triangle ABC is similar. This is the sign of similar to the small right triangle APE according to angle similarity rule. And for the fact that the right big triangle ABC is similar to the right small triangle APE, we will derive that the following relationship exists between their sides. We will derive that side AP of the right triangle APE over side AB of the right big triangle ABC is equal to side AE of the right triangle APE over side AC of the right big triangle ABC. Repeat again, we will derive that side AP of the right triangle APE over side AB of the right big triangle ABC equals to side AE of the right triangle APE over side AC of the right big triangle ABC. AP is 6, according to what is given as the equation, over AB. AB is the missing side, so we leave it as it is. And it is equal to AE. AE is the diameter of this semicircle, that is equal to 2x. With the other side, the diameter is of course 2x. Over AC. AC in total equals to 6 plus 5, that is 11. So in total, if you found out that 6 over AB equals to 2x over 11. Here we cross multiply this equation, and we get that 6 times 11 is 66, and it is equal to 2x times AB. So 666 equals to 2x times AB. Here we will divide this equation by 2, and we get that 66 over 2 is 33, equals to 2x over 2 is x, so in total this expression equals to x times AB. In total we found out that 33 equals to x times AB. Here we will divide this equation by x, and you get that AB equals to 33 over x units in its length. So if we found out that the length of this side AB of rectangle ABCD is equal to 33 over x units. Our mission is to find out the area of this rectangle ABCD. So actually we know that the area of any rectangle equals to the length of the rectangle times the width. But again, the area of any rectangle equals to the length of the rectangle times the width. And therefore, the area of this rectangle ABCD must be equal to the length of rectangle ABCD times the width. The length is AB. The length of rectangle ABCD is AB. And the width is CB. So to that we found out that the area of rectangle ABCD is equal to AB times CB. AB is 33 over x over CB. CB is x. So we have here x in the numerator and x in the denominator, so x will get cancelled, and we left only with 33. So if we found out the area of this rectangle ABCD is equal to 33 square units. And that is the answer to the question. I repeat again, the area of this rectangle ABCD is equal to 33 square units. So we finish with the first question. In the next step, I'll present through the second question, and we will solve the second question of this lecture. Our mission in this second question is to find out the area of this green shape. So in the drawing, we have square ABCD. We know that this is line segment BP, that is equal to line segment PC, and we also know that the area of triangle OCP is equal to 5 square units. Again, our mission is to find out the area of this green shape. So first of all, we define the length of this line segment BP as A, and because of the fact that BP equals to PC according to what is given as the equation, PC must be also equal to A. And we know that all the sides of any square are equal to each other, so BC in total equals to A plus A, that is 2A, therefore AD must be also equal to 2A units in its length. Those two angles are defined as vertex angles, and know that vertex angles are equal to each other. So if we define this angle as theta, then the size of this angle must be also equal to theta, because they are equal to each other according to the rule that I mentioned. We also know that the opposite sides of a square are parallel to each other. So in square ABCD, side AD is parallel to side BC. Those two angles are defined as alternating angles, and are located between the parallel AD and BC, and therefore they are equal to each other according to Rule 15. Rule 15 says that alternating angles between parallel lines are equal to each other. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha, because they are equal to each other according to Rule 15. Likewise, those two angles, they are also defined as alternating angles, and they are located between the same parallel lines AD and BC, and therefore they are equal to each other according to Rule 15. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta, because they are equal to each other according to Rule 15. So it is very easy to see that the small triangle COP is similar to the big triangle AOD according to angle similarity rule. In both triangles we have angle alpha, in both triangles we have angle theta, and in both triangles we have angle beta. Therefore, those two triangles are similar to each other according to angle similarity rule. So write it down. The big triangle AOD is similar, this is the sign of similar, to the small triangle COP, according to angle similarity rule. And from the fact that those two triangles are similar to each other, actually I will present to you a new rule that is related to similar triangles, and we will implement the new rule in our drawing on those two similar triangles, AOD and POC. The new rule is Rule 22. According to Rule 22, the ratio of the areas of similar triangles is equal to the square of the ratio of their corresponding sides. Again, the ratio of the areas of two similar triangles is equal to the square of the ratio of their corresponding sides. So in the drawing we have those two triangles, triangle ABC and triangle DEF. Those two triangles are similar to each other, and according to this rule 22, the ratio between the areas of those two triangles, that is to say the area of triangle ABC over the area of triangle DEF, is equal to the square of the ratio of their corresponding sides. So in these two triangles, side AC is the corresponding side of side DE. Likewise, side AB is the corresponding side of side DF. And finally, side CB is the corresponding side of side EF. So the ratio of the areas of the similar triangles is equal to the square of the ratio of their corresponding sides. Side AC is the corresponding side of side DE. The square of the ratio of side AC with side DE is AC over DE squared. So in total we found out that the ratio between the areas of those two similar triangles is equal to the square of the ratio of their corresponding sides. That is to say, it is AC squared over DE squared. Likewise, side AB is the corresponding side of side DF. And the square of the ratio of those two sides is equal to AB over DF squared. So the area of triangle ABC over the area of triangle EDF also equals to AB over DF squared. And finally, side CB is the corresponding side of side EF. So the square of the ratio of those two corresponding sides is equal to CB over EF squared. So in total, we have found out that the area of triangle ABC over the area of triangle EDF is equal to CB over EF squared. Okay, so we can implement rule 22 in our drawing, because in our drawing we have only found out that the big triangle ADO is similar to this small triangle, triangle OPC. According to rule 22, the ratio between those two similar triangles, that is to say, the ratio between the areas of those two similar triangles, that is to say, the area of this triangle ADO, the area of the big triangle ADO, over there of this triangle POC, this expression is the ratio between the areas of those two triangles, and that is the ratio of the areas of those two triangles, and it is equal to the square of the ratio of their corresponding sides. On those two triangles, ADO and COP, side AD is the corresponding side of side PC. The square of the ratio of those two corresponding sides is of course AD over PC squared. AD over PC squared is the square of the ratio of their corresponding sides. So in total, we actually found out that the ratio between the areas of triangle ADO and triangle POT is equal to the square of the ratio of their corresponding sides. So this equation is the implementation of rule 22 in our two similar triangles, AOD and POC. The area of triangle AOD is unknown, so we leave it as it is. Over the area of this triangle POC, it is given as the question that the area of this small triangle POC is equal to 5 square units. So we substitute the area of triangle POC by 5, and it is equal to AD over PC squared. AD is 2A, over PC, PC is A, squared. Here we have A in the numerator and A in the denominator, so A will get cancelled, and we left only with 2 squared. This is of course 4. So in total, if we found out the area of triangle AOD the area of the big triangle AOD over 5 equals to 4. So here we multiply this equation by 5, and we get that the area of the big triangle AOD is equal to 5 times 4, that is 20 square units. So if we found out the area of this big triangle AOD is equal to 20 square units. Because of the fact that those two triangles are similar to each other, the following relationship exists between their sides. Side AD of the big triangle ADO over side PC of the small triangle POC is equal to side AO of the big triangle ADO over side OC of the small right triangle POC. And again, because of the fact that those two triangles are similar to each other, the following relationship is between the sides. The side AD of the big triangle ADO over side PC of the small right triangle POC is equal to side AO of the big right triangle AOD over side OC of the small right triangle POC. AD is 2A over PC. PC is A, and it is equal to AO over OC. So if we found out that 2A over A equals to AO over OC. Here we have A in the denominator and A in the denominator, so if it cancels, we are left only with 2. So 2 equals to AO over OC. Here we multiply this equation by OC, and we get that two times OC equals to AO. So if we define the length of side OC as B, so we can substitute OC by B, and we get that 2B equals to AO. So if OC equals to B, then AO equals to 2B. That is to say, AO is twice as long as OC. So, in total, if we found out that if OC equals to B, then AO equals to 2B. If OC equals to B, according to the definition, then AO will be equal to 2B. So, in the next step, I will present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule 23. According to rule 23, first of all, rule 23 is true in any triangle. So this is triangle ABC that could be in a triangle. So in triangle ABC, we draw the red line segment AP. By drawing the red line segment AP, we divided this triangle ABC into two parts, or into two smaller triangles. The first triangle is APP, and the second triangle is APC. Rule 23 talks about the smaller triangles that will be created by drawing line segment AP from the vertex A in triangle ABC. According to rule 23, the ratio between the areas of those two smaller triangles will be equal to the ratio between their corresponding bases. So the area, what is the ratio between the areas of those two small triangles? Actually, the area of this small triangle APC is the base PC times the height that is edge over 2. Again, it is the base BP times the height edge over 2. So in total, the area of this small triangle ABP equals to the base BC times the height edge over 2. Likewise, the area of this small triangle APC is equal to the base PC times the height edge over 2. Actually, both those two small triangles have the same height that is edge. So the area of this small triangle PCA equals to the base PC times the height that is edge over 2. So it is PC times edge over 2. And what is the ratio between the areas of those two small triangles? It is the ratio between those two expressions, of course. So it is BP times H over 2 over CP times H over 2. So we have 1/2 in the numerator and 1/2 in the denominator, so 1/2 will get cancelled. Here we have H in the numerator and H in the denominator, so H also will get cancelled, and we're left only with BP over CP. So we found out that the ratio between the areas of those two small triangles is equal to the ratio between their bases. Why? Because the base of this small triangle ABP is BP over CP. CP is the base of this small triangle APC. Repeat again, we found out that the ratio between the areas of those two small triangles is equal to the ratio between their corresponding bases. That is BP over PC. So we can actually implement rule 23 in our drawing. Why? Because in our drawing, this is the big right triangle ADC. This big right triangle ADC has been divided into two parts by line segment OD. Repeat again. The big right triangle ABC has been divided into two parts by line segment OD. So all the requirements of rule 23 are satisfied, and therefore we can implement rule 23. According to rule 23, the ratio between those two smaller triangles that were created by line segment OD is equal to the ratio between their corresponding bases. That is to say, it is AO over OC, because the base of triangle ADO is AO and the base of triangle DOC is OC. So the ratio between the areas of those two small triangles is equal to the ratio between their bases, that is AO over OC. So I write it down. We actually found out that the ratio between the areas of those two triangles is of course the area of triangle ADO over the area of triangle DOC. So in the right triangle, triangle ADO, according to rule 23, the following equation is true: that the ratio between the areas of those two small triangles, that's actually, the ratio is the area of triangle ADO over the area of this triangle, triangle DOC. Repeat again, those two small triangles were created by drawing line segment OD in this right triangle, triangle ADC. So the ratio between the areas of those two triangles is equal to the ratio between their corresponding bases. The two bases are AO of triangle ADO and OC of triangle DOC. So it is AO over OC. That is the ratio between their corresponding bases. This equation is the implementation of rule 23 in our drawing, actually in the right triangle, triangle ADO. Again, the ratio between the areas of those two triangles, that is actually the area of triangle ADO over the area of triangle DOC, equals to the ratio between their corresponding bases. That is actually AO over OC. The area of triangle ADO over the area of triangle DOC, that is the ratio between the areas of the two small triangles, is equal to the ratio between their bases, that is AO over OC. The area of this triangle ADO is 20 square units, so substitute the area of triangle ADO by 20 over the area of this triangle, triangle DOC. The area of this triangle DOC is unknown, so we leave it as it is. It is the area of triangle DOC that is unknown, and it is equal to AO. AO is 2B over OC. OC is B. So in total it is 2B over B. We have B in the denominator and B in the denominator, so B will get cancelled, and we left only with 2. So in total we have found out that 20 over the area of small triangle DOC is equal to 2. So here we will multiply this equation by the area of triangle DOC. And we get that 20 equals to 2 times the area of triangle DOC. Here we divide this equation by 2, and you get that the area of the small triangle DOC is equal to 20 over 2 is 10. So the area of triangle DOC is equal to 10 square units. So actually this is triangle DOC, and the area of this small triangle DOC is equal to 10 square units. The big right triangle ABC can go into this small right triangle ADC according to side rule. I repeat again, the big right triangle ABC can go into the big right triangle ADC according to side rule. Why? Because we know that ABCD is a square and all of its sides are equal to each other. So why those two right triangles can go into each other? First of all, side AB of triangle ABC is equal to side DC of triangle ADC, because it is a square, ABCD is a square. Likewise, side BC of triangle ABC is equal to side AD of triangle ADC because of the same reason. And finally, side AC is the common side that belongs to both triangles. So therefore, triangle ABC can go to triangle ADC according to side rule. All the three sides of triangle ABC are correspondingly equal to all the three sides of this triangle ADC. So I write it down. I found out that the right triangle ABC congruent, this is the sign of congruent, to the right triangle ADC according to side rule. And from the fact that those two right triangles can go into each other, we will derive that they have also the same areas. Any two triangles that can go into each other, they must have also the same areas. So, from the fact that triangle ABC can go into triangle ADC, we will derive that the area of triangle ABC is equal to the area of triangle ADC. Again, from the fact that triangle ABC can go into triangle ADC, we derive that the area of triangle ABC is equal to the area of triangle ADC. But it is very easy to see from the drawing that the area of this right triangle ADC, in total it is equal to 20 plus 10, it is 30 square units. So can I say that the area of triangle ADC is equal to 30 square units, and from this equation the area of triangle ABC equals to the area of triangle ADC equals to 30, we will derive that the area of triangle ABC is also equal to 30 square units. The area of the triangle ABC is also equal to 30 square units from one side, but from the other side, if we define the area of this green shape, that is the area that we are looking for in this question, as x, that is to say, the area of this green shape is equal to x square units according to our definition, then the total area of the right triangle ABC will be equal to x plus 5 square units. So from the other side, the area of this triangle ABC in total it is equal to x plus 5 square units. So from the other side, the area of triangle ABC is also equal to x plus 5 square units. And from this equation, x plus 5 equals to the area of triangle ABC equals to 30. We will derive that x plus 5 equals to 30. Here we subtract 5 from this equation, and we get that x equals to 30 minus 5 is 25 square units. So if we found out that the area of this green shape is equal to 25 square units. So finished with the second question. In the next step, I'm sorry, the lecture, we'll start with the first question, of course. In the first question, our mission is to find out the area of this rectangle ABCD. So in the drawing, we have the big rectangle ABCD. Inside this rectangle, we have this semicircle. In addition, we know that this is called AP, that is equal to 6 units in itself. This is line 7 PC, that is equal to 5 units in itself. Again, our mission is to find out the area of this big rectangle ABCD. So first of all, we define, because of the fact that ABCD is a rectangle, all those 4 angles are right angles. The next step, we define the center of this semicircle as O, this point is O. We define the radius of this semicircle as X. And point O is the center of the semicircle, point A is the point of the semicircle itself, therefore OA is the radius of the semicircle that is equal to x units in its length according to our definition. Likewise, OE is also the radius of the semicircle that is equal to x. We join points O and M together by straight line. OM is of course also the radius of this semicircle that is equal to x. And because of the fact that the radius OM of this semicircle that is equal to x, the radius OM is drawn to point M, that is the point of tendency of tangent DC with this semicircle, and whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If DC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. By doing this construction, you can deduce the small quadrangle DMOA. Inside this small quadrangle DMOA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 free triangle. In total, they must be equal to 360 degrees according to the rule that says that the sum of the angles in any triangle is equal, the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, this 4 free triangle must be equal to 90 degrees in its size. So quadrangle DMOA has 4 right angles. And according to rule 5, any quadrangle that has 4 right angles must be this rectangle in front of the square. So we have to this quadrangle DMOA as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So rectangle DMOA, side MO must be equal to the opposite side DA. But MO is x, therefore the opposite side DA must be also equal to x units in its length. In the big rectangle ABCD, the opposite sides must be also equal to each other. That is to say, side AD must be equal to the opposite side CB. But AD is x, therefore CB must be also equal to x units in its length. In the next step, we join points P and E together by straight line. By joining points P and E, we get a peripheral angle APE. Peripheral angle APE subtend on AE, that is the diameter of this semicircle, and according to rule 7, any peripheral angle that subtends on the diameter of the circle or semicircle must be equal to 90 degrees in size. Therefore, this peripheral angle APE is equal to 90 degrees according to rule 7. In the next step, we define this angle as alpha. In the right angle APE, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first angle must be equal to 90 degrees minus alpha. 1 equals 90 degrees minus alpha plus alpha is 90 degrees. And 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in the triangle. Likewise, in the big right angle ABC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first angle must be equal to 90 degrees minus alpha. According to the sum rule, that says that the sum of the angles in the triangle is equal to 180 degrees. In the next step, we proved that the big right angle ABC is similar to this small right triangle APE. So why those two right triangles are similar to each other? First of all, this is angle A, that is a common angle that belongs to both triangles. So we can write down that angle A equals to itself is a common angle that belongs to both triangles. In addition, those angles are both equal to 90 degrees. They are both equal to 90 degrees, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So in total, if you found out that all the triangles of the right big triangle ABC are correspondingly equal to all the triangles of this right triangle APE. Therefore, those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. That side AP of the right triangle APE over side AB of the right big triangle ABC equals to side AE of the right triangle APE over side AC of the right big triangle ABC. And then again, remember that side AP of the right triangle APE over side AB of the right big triangle ABC equals to side AE of the right triangle APE over side AC of the right big triangle ABC. AP6 according to what is given us in question. AB is the missing side, so we leave it as it is. AE is the diameter of the semicircle, that is 2x over AC. AC in total is 6 plus 5, that is 11. So in total, we have found out that 6 over AB equals to 2x over 11. Here, of course, multiply this equation, and finally found out that 6 times 11 is 66, and this is equal to 2x times AB. Here we divided this equation by 2 and finally found out that 666 over 2 is 33. So 33 equals to 2x over 2 is x. So in total this expression equals to x times AB. So in total we found out that 33 equals to x times AB. Here we divided this equation by x and finally found out that AB equals to 33 over x. So side AB of this rectangle ABCD is equal to 33 over x units in its length. Our mission is to find out the area of this rectangle ABCD. We have to find out the area of rectangle ABCD. Actually, we know that the area of a rectangle equals to the length of the rectangle times the width. And therefore, the area of this rectangle ABCD must be equal to the length of this rectangle ABCD times the width. Okay, so the length of this rectangle ABCD is AB and the width is CB. So in total, the area of rectangle ABCD must be equal to the length AB times the width CB. So it is AB times CB. AB is 33 over x and CB is x. So in total, the area of rectangle ABCD must be equal to 33 over x times x. We have x in the numerator and x in the denominator, so x will get cancelled and we left only with 33. So in total, if we found out that the area of this rectangle ABCD is equal to 33 square units. We finish with the first question. In the next step, I present the rule of the second question and we solve the second question of this lecture. In the second question, our mission is to find out the area of this ring shape that is inside square ABCD. So, in the drawing, we have square ABCD, We also know that BP equals to line 7 BP equals to line 7 PC. This is triangle OPC. The size of this triangle OPC is 5 square meters. Again, our mission is to find out the area of this green shape. So first of all, we define the length of this line 7 BP is A. Because of the fact that BP equals to PC, if BP is A, then PC must be also equal to A. We know that all the sides of a square are equal to each other. BC is A plus A, that is 2A, therefore the other side AD of this square CD must be equal to 2A units in its length. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if we define this angle as theta, then this angle must be also equal to theta because they are equal to each other according to the rule that I mentioned. We know that the opposite sides of a square are parallel to each other. So in square ABCD, side AD is parallel to the opposite side BC. Those two angles are defined as alternating angles and are located between the parallel lines AD and BC. And therefore, they must be equal to each other according to rule 15. So if the side of this angle is alpha, then the side of this angle must be also equal to alpha because they are equal to each other according to rule 15. Likewise, those two angles are also defined as alternating angles and they are located between the same parallels PC and AD, and therefore they are equal to each other according to rule 15. So if we define the side of this angle as beta, then the side of this angle, must be also equal to beta because they are equal to each other according to rule 15. So in total, if we found out that the area of this big triangle AOD, actually that the triangle AOD is similar to this small triangle COP according to angle similar to rule. In both triangles we have angle alpha, in both triangles we have angle theta, in both triangles we have angle beta. So those two triangles are similar to each other according to angle similar to rule. In the next step, I presented to you a new rule that is related to two similar triangles, and we implemented the new rule in our drawing on our those two triangles that are similar to each other. The new rule is rule 22. According to rule 22, the ratio of the areas of similar triangles is equal to the square of the ratio of their corresponding sides. So in the drawing we have those two triangles, triangle ABC and triangle DEF, that are similar to each other, and according to this rule 22, the ratio between the areas of those two similar triangles is equal to the square of the ratio of their corresponding sides. So the ratio between the areas of those two triangles is the area of triangle ABC over the area of triangle EDF. And that ratio equals to the square of the ratio of their corresponding sides. On those two similar triangles, side AC is the corresponding side of side DE, side AB is the corresponding side of side DF, and side CB is the corresponding side of side EF. So the ratio of their corresponding sides, the square of the ratio of their corresponding sides is as follows. AC, side AC is the corresponding side of side D. So the square of the ratio of those two corresponding sides is of course AC over DE squared. Likewise, side AB is the corresponding side of side DF. So the square of the ratio of those two corresponding sides is of course AB over DF squared. And finally, side CB is the corresponding side of side EF, and the square of the ratio of those two corresponding sides is of course CB over EF squared. Okay, so I can actually implement rule 22 in our drawing. Why? Because in our drawing, we only found out that the big triangle ADO is similar to this small triangle OPC. Therefore, we can implement here rule 22. According to rule 22, the ratio of those two similar triangles, that is to say, the area of triangle ADO over the area of triangle POC, that is the area between the similar triangles, and that is the ratio of those two, the ratio between the areas of those two similar triangles, that ratio is equal to the square of the ratio of their corresponding sides. Side AD is the corresponding side of side PC. Side AD of triangle ADO is the corresponding side of, to side PC of triangle POC. So the square of the ratio of those two corresponding sides is of course AD over PC squared. So in total, the area between the ratio between the areas of the two similar triangles is the area of triangle ADO over the area of triangle POC, and that ratio is equal to the square of the ratio of their corresponding sides. That is to say, it is AD over PC squared. The area of triangle ADO is unknown, so we leave it as it is. Over the area of triangle POC. The area of triangle POC is 5, so we substitute the area of triangle POC by 5, and it is equal to AD. AD is 2A, and PC is A. Again, AD is 2A, and PC is A. We have A in the numerator and A in the denominator, so A in the denominator, so A will get cancelled, and we have 2 with 2 squared, that is 4. So in total we found out that the area of triangle AD over 5 equals to 4. And we multiplied this equation by 5 and finally found out that the area of the big triangle AOD is equal to 5 times 4, that is 20 square units. Again, the area of this big triangle ADO is equal to 20 square units. Because of the fact that those two triangles are similar to each other, the following relationship exists between their sides. Side AD of triangle ADO or side PC of triangle POC is equal to side AO of triangle ADO or side OC of triangle POC. Repeat again. Side AO of triangle ADO over side PC of triangle POC equals to side AO of triangle AOD over side OC of triangle POC. AD is 2A, PC is A. We have A in the numerator and A in the denominator, so A will get cancelled. So in this of the equation we have to leave 2. So 2 equals to AO times OC. If we multiply this equation by OC, and finally found out that 2 times OC equals to OA. 2 times OC equals to OA. We define the length of side OC as B, and we substitute OC here by B, and found out that OA equals to 2B. So if the length of side OC is B, then the length of side OA is 2B. That is to say, OA is twice as long as OC. Okay, so in the next step, I presented to you a new rule and implemented the new rule in our drawings. The new rule is rule 23. Rule 23 is true in any triangle. This is triangle ABC that could be any triangle. This triangle ABC, if we draw the red line segment AP, it will divide this triangle ABC into 2 parts. The first part, or in two smaller triangles. The first small triangle is ABP, and the second small triangle is triangle APC. Again, the first triangle is ABP, and the second triangle is APC. According to this rule 23, the ratio between the areas of those two small triangles that were created by line segment AP, the ratio between the areas of those two small triangles is equal to the ratio between their corresponding bases. The corresponding bases is BP and PC. Therefore, the ratio between the areas of those two small triangles is equal to BP over PC. Again, the ratio between the areas of the smaller triangles is the area of triangle ABP over the area of triangle APC. That ratio is equal to the ratio between their corresponding sides, that is actually BP over PC. Okay, actually, how we arrive to this expression, because we have the area of triangle ABP is equals to the base BP times the edge over 2. This triangle APC is equals to the base PC times the height that is edge over 2. So the ratio between the areas of those two triangles is equal to the ratio between those two expressions. the ratio between those two expressions is as follows. We have one half in the numerator and one half in the denominator, so one half will get cancelled. Likewise, we have edge in the numerator and edge in the denominator, so edge also gets cancelled, and we have to leave with BP over CP. So in total, we actually found out that the ratio between the areas of those two small triangles is equal to the ratio between their corresponding bases. That is to say, it is BP over CP. So whenever you draw, you take any triangle ABC, could be any triangle. Could be any triangle. If you draw the red line segment AP, it will divide the triangle into small triangles. Then the ratio between those two small, the ratio between the rest of those two small triangles will be equal to the ratio between their corresponding bases. That is to say, it will be equal to BP over CP. So you can actually implement Rule 23 in our drawing. In our drawing, this is the right triangle ADC. Line segment OD divides the big triangle ADC into two smaller triangles, triangle ADO and triangle ODC. So all the requirements of Rule 23 are satisfied, and therefore we can implement Rule 23. According to Rule 23, the ratio between the areas of those two smaller triangles, that is to say, the area of this triangle ADO over there triangle DOC, the area of the small triangle ADO over there of the small triangle DOC is equal to the ratio between their corresponding bases. The base of this triangle ADO is AO, and the base of this triangle DOC is OC. And the ratio is AO over OC. It is equal to AO over OC. So the ratio between the areas of the two small triangles is equal to the ratio between their corresponding bases. That is AO over OC. The area of triangle AOD is 20. So substitute the area of triangle AOD by 20 over the area of triangle DOC. The area of this triangle DOC is unknown, so we left it as it is. And it is equal to AO over OC. AO is 2A, OC is A. So it is AO is 2B, and OC is B. Again, AO is 2B and OC is B. We have B in the numerator and B in the denominator, so B will get cancelled, and the left only with 2. So in total, we actually found out that 20 over the area of triangle DOC equals to 2. We multiplied this equation by the area of triangle DOC, and finally found out that 20 equals to 2 times the area of triangle DOC. We multiplied this equation by the area of triangle DOC and found out that 2 times the area of triangle DOC equals to 20. Here we divided this equation by 2 and finally found out that 20 over 2 is 10. So the area of triangle DOC is equal to 10 square units. This is triangle DOC, this triangle DOC is equal to 10 square units. Triangle ABC, the right triangle ABC is similar to this triangle ADC according to side rule. That is to say, side AB of triangle ABC equals to side DC of triangle ADC. Likewise, side BC of triangle ABC is equal to side D of triangle ADC. Why? Because it is a square and all the sides of the square are equal to each other. And finally, side AC is a common side that belongs to both triangles. So we can write down that side AC equals to itself as a common side that belongs to both triangles. So in total, those two triangles can go to each other according to side rule. The triangle ABC can go into triangle ADC according to side rule. And from the fact that the two triangles can go into each other, we will derive that they are also the same areas. That is to say, the area of triangle ABC is equal to the area of triangle ADC. So those two triangles have the same areas. Repeat again. We have found out that the area of the right triangle ABC is equal to the area of the right triangle ADC. But we know that the area of this right triangle ADC in total equals to 20 plus 10, that is 30 square units. So we can write here that the area of triangle ADC equals to 30 square units. And from this equation, the area of triangle ABC equals to the area of triangle ADC equals to 30. We will derive that the area of triangle ABC is also equals to 30 square units. From one side, but from the other side, if we define the area of this ring shape as x, that is to say the area of this ring shape is equal to x square units according to our definition, then the total area of triangle ABC will be equal to x plus 5 square units. So from the other side, the area of triangle ABC is also equal to x plus 5 units. X plus 5 square units. And from this equation, x plus 5 equals to the area of triangle ABC equals to 30 square units. We derive that x plus 5 equals to 30. Here we subtract 5 from this equation and finally found out that x equals to 30 minus 5, that is 25. X is the area of the green shape. So in total, we have found out the area of this green shape is equal to 25 square units. Okay, thank you very much.